Okay, in this session we're going to be looking at the design of control systems, analog and digital systems, using compensation techniques. It's an introductory unit, so it's a bit of an overview in actual fact of some basic technique. There are other techniques, but we're going to concentrate on just giving you some introductory information and experience of that. All right. The other techniques that involve improving that transient response via cascade compensation, improving steady state error, and the transient response and feedback compensation. So we're going to concentrate on improving the steady state error via a cascade compensation technique. So the objective is to improve the steady state error without appreciably affecting the transient response. What we're going to do is adopt a technique we've used before, the root locus technique. And basically that approach relies upon that basic characteristics of the transient response of a closed loop system being closely related to the location of the closed loop poles, which are the roots of your closed loop system, found through getting your characteristic equation, which is on the denominator of your transfer function, and then equating that to 0 if we want to find the roots, or going through and using other techniques to help us find information with Howards and that thing. If the system has a variable loop gain, then the location of the closed loop poles depends upon the value of the loop gain chosen. It's important to know that the closed loop poles move in the S-plane as the loop gain is varied. From a design perspective, simple gain adjustment may move the closed loop poles to desired locations. However, the design problem then becomes the selection of an appropriate gain value. If the gain adjustment alone does not yield a desired result, then the addition of a compensator to the system will be necessary. So the sketch of the root locus is a plot of the roots of the characteristic equation of the closed loop system for all values of a system parameter using usually the gain. However, any other variable of the open loop transfer function may be used. We're going to concentrate on gain. By adopting this method, the designer can predict the effects on the location of the closed loop poles of varying the gain value or adding open loop poles or indeed open loop zeros. So underlying the principle is the root locus. So therefore then all those principles that we talked about and actually already done with regards to the root locus will come into play. So we'll have to sketch out the root locus and have a look at it. Also keeping in mind that all those underlying mathematics, the angular contribution, looking at where the poles and zeros are, what happens to the function overall in terms of the root locus. So nothing new in that regard. So the values of S that make the open loop transfer equal to -1 must satisfy that characteristic equation of the closed loop system. The root locus sketch clearly shows the contributions of each open loop pole and 0 to the locations of the closed loop poles. The root locus sketch also shows the manner in which the open loop poles and 0 should be modified so that the response meets system performance specifications, settling time, anything like that that might have to come into the design characteristics. Now, the general effects of the addition of poles is that it pulls the root locus to the right, which lowers the system's relative stability and consequently slows down the settling of the system's response. So slows down the settling time. While the general effects of the addition of zeros is to pull the root locus to the left, which makes the system more stable and consequently speeds up the settling time of the system's response. There's two methods. Method 1 is the ideal integrated compensator, or what we call PI, and the method 2 is the lag compensation. As I say, it's in introductory units. We're going to concentrate on method 1, the ideal integrated compensation technique, PI. Now, this technique uses a pure compensator to position an open loop forward path pole at the origin. And in this way, it increases the system type and reduces the steady state error to 0. For example, a system 0 system responding to a step input with a finite error responds with 0 error if the system type is increased by 1. Active circuits, things like diodes, transistors, op-amps, SCRs, they are anything that has the ability to control electron flow, can be used to place poles at the origin. The ideal integrator compensator is termed a proportional plus integrator or a PI control. This results because the process involves fitting the error, proportional, plus the integral of the error forward to the plant. So again, if we're looking at your basic control system with unity feedback here, then we're talking about the gain, some transfer function for the plant. We were able to plot out the root locus. In particular, we're going to concentrate on, to begin with, that angular contribution that will help us start setting up the whole process. All right, now, in order to see how to improve the steady state error without affecting the transient response, we'll be investigating that particular setup, the root locus, as you see in figure A. Here we have a system operating with a desirable transient response generated by the closed loop poles at A. Now, if we add a pole at the origin to increase the system type, then the angular contribution of the open loop poles at point A no longer 180 degrees, because you've changed the particular parameters. And the root locus no longer goes through point A as demonstrated by figure B. Okay, so now we will talk about positioning and the compensator, as you can see there, and we'll draw out a further discussion with regards to the effect of that. Now, from our discussion previously of steady state errors, then if we consider the relationship between the input signal, the system itself, the static error, and the steady state error, then for a type 0 system, it has a finite error for step input. Now, when we increase from type 0 by one type into a type 1 system, then the error becomes 0 for the step input. So that information and that table you've seen beforehand when we've been discussing steady state systems, or whatever input, whether it's a step ramp, or a parabolic input. Now, to solve the problem, we also add a 0 close to the pole at the origin. Okay, so therefore then our compensator changes slightly. So our K on S originally now becomes K into S plus 1 on S to take the pole and the 0 into consideration at close to the origin. That's the 0 I'm talking about. We add that 0 close to the pole, that's at the origin. Okay, so again, we'll be investigating that angular contribution. Now, the angular contribution of the compensator 0 and compensator pole cancel out, point A. Still on the root locus, and the system type has been increased. Furthermore, the required gain at the dominant pole is about the same as before compensation, since the ratio of the lengths from the compensator pole and the compensator 0 is approximately equal to 1. Thus, we've improved the steady state error without appreciably affecting the transient response. So a compensator with a pole at the origin and a 0 close to the pole is called an ideal integral compensator. So in this following example, the effect of the ideal integral compensation is going to be demonstrated. Now, it looks a bit involved, but basically it's all like all these things. Just follow through the process. There's all the mathematical background arising from root locus, because that's the fundamental technique or mathematical process that's occurring. An open loop pole will be placed at the origin to increase the system type and drive the steady state error to 0. An open loop 0 will be placed very close to the open loop pole at the origin, so that the original closed loop poles on the original root locus will still remain at approximately the same points on the compensated root locus. Okay. Okay, because we don't want to change that transient response very much. So, the following unity feedback system operates with a damping ratio of 0.174 and a step unit input. And as we see, we also have unity feedback. So let's process a bit more. We've said that we're going to analyze, as we see in figure B, we're going to put in the addition of the ideal integral compensator, and we'll reduce that steady state error to 0 for a step unit input without appreciably affecting that transient response. All right, so here's our compensator, and let's explore that a little bit more. Now, we know from the root locus, the poles will always move towards the zeros. That's what always happens. It's the basic characteristic underlying root loci. When introducing a pole at the origin, obviously we change the transient response. So in order to undo the change and still maintain the increase in system type, we'll need to put a 0 very close to the compensator pole, basically, to counteract it. Both the 0 angle and the pole angle will cancel each other, thus making the root locus resemble the original root locus, but with an increase in system type, and we call that pole 0 cancellation. So keeping this process in mind, the compensating network is chosen with a pole at the origin to increase the system type and a 0 at negative 0.1. So that's our general form. And of course, when we're looking at our 0, we look at the numerator. So if we equate that to 0, we can see why that's S equals to negative 0.1. Now, that's chosen close to the compensator pole so that the angular contribution of the compensator evaluated at that original dominant second order poles is approximately 0. So consequently, the original second order closed loop poles are still approximately on the new root locus. So we're going to go back and begin the process by first analyzing the uncompensated system and determine the location of the dominant second order poles. So if we look at our original function, we've got a plant g of s equal to 1 divided by those factors s plus 1, s plus 2, and s plus 10. With a step unit input, standard R of s equals 1 on s. So this results in a steady state error. So that's just a steady state error formula. Plug in our particular characteristic transient functions and our step input, and we end up with a steady state error of about 0.9524. Remembering working in 4 decimal places just so that we can keep track of things, and it means you can compare with my values much more easily with regard to round-off figures and things. Now, we were told that the damping ratio is going to be 0.174. We know that there's a step unit input, so we can calculate the overshoot. So plug it in the normal formula, simplify it, and we find that the overshoot for that particular damping ratio and step unit input is 57.40%. Okay. So the first thing we need to do is to generate the root locus using the process that we've done previously. And then we'll need to combine the range of information derived from the following analysis and mark it on the root locus. Keeping in mind we're dealing with a unit feedback system. So like always, we'll go back, find this typical feedback system, keeping in mind that this is our plant, unity feedback, so the usual process, and we'll end up with that expression. And again, we're interested in the polynomial on the bottom, or the characteristic equation. And as we can see, once we multiply that out, rearrange it, we end up with P of S, the characteristic equation, equals S cubed plus 13S squared plus 32S plus 20 plus K. All right. Now, we're also looking back at our design parameters, and one specification was the damping ratio was 0.174. So again, looking at the underlying mathematics from the root locus, we can go about looking at that angular contributions. So here the angle for the compensator is going to be equal to 180 minus the angle for that particular controller. So plugging in our values, we see that that's about 100.02 degrees. So the dominant closed loop poles are located at the intersection of the root locus and the damping ratio line. In order to determine this intersection point, note that the damping ratio is a linear function such that y equals negative mx plus c. So that's just a general equation for a straight line with a negative slope. So therefore then, if I have b equals negative ma plus c, the slope is negative orientation as I mentioned, and the damping ratio line passes through the origin, so then c must just equal 0. So therefore then y equals negative mx, so in our case it's going to be b equals negative ma. Now keep in mind that really what do they equate from a general expression, y equals negative mx, to in terms of our imaginary real axes that we have when we're doing the root locus? Well, b is the imaginary part of the intersection point, and m is the slope of the damping ratio. A is the real part of that intersection point. So if we consider the slope of the damping ratio, again, just from the basic definition given quite some time ago, the damping ratio, slope for that damping ratio is m equals the tan of the arc cosine of the damping ratio. Evaluate that, and we end up with 5.6594. Now, consequently, from our little expression, b equals, again, negative m times a, then b must equal negative 5.6594 times a. So now we've got two unknowns. We've already found our slope, that's great, so we've got to go and find our a and b values. So if we search along that damping ratio line, all this next part that we're discussing about all comes from the root locus fundamental underlying mathematics. So searching along that damping ratio line, we can determine the dominant closed loop poles are located at the intersection of the root locus and the damping ratio line at the point which yields a summation of those angles, particularly the zero angles and the pole angles, equal to an odd multiple of 180 degrees. So as a consequence, we can conclude that the point is on the root locus. The gain at this point is then found by multiplying the pole lengths drawn to that point and dividing by the product of the zero lengths drawn to that. Again, they're little equations from the root locus. So we can, so that's mathematically what we're looking at. If we represent them in the diagram, here's my damping ratio. As we go through, here's my poles. So therefore then we can investigate the dominant closed loop poles being located at the intersection of the root locus and the damping ratio. So when we do that, we can find these little angles in here, which we can do with trigonometry by using the arc tangent. So we end up with this expression relating the arc tangent of each of those, and obviously it has to add up to the odd multiple of 180 degrees. And we already know what our three poles are, because we know the factors from the characteristic equation are s plus 1, s plus 2, and s plus 10. So we can plug in our P1, P2, and P3 values. And what we end up with, of course, now is an expression with A's and B's in it. We can look at that expression and take into account some of our identities. This is the arctan identity for expansion when you have that kind of format. So then we can take that into account. And what I'm going to do is make life a little bit easier. So if we set A equal to this particular, this is called the argument of that particular expression, and this argument equal to B, and that argument equal to C, then we can go about applying, in this particular case, this arctangent identity. And as you can see, once we plug in our values, our expression, we can start to take that identity, put it into that particular form from the identity, and keep working through. So now I'm going to let D equal that, and then as you see, just follow through. We now end up with this expression. We can use our arc identity again, and we find that we can keep going, basically follow the mathematics, until we get an expression, and then we can do some back substitution and just keep solving our problem. So back substitution again, just follow through the mathematics. It's the best thing to do is to work through these yourself. You don't learn mathematics by watching, so the best thing is to use this as a guide to follow through the processes. But essentially what we do, yes, follow through. So we're going to end up with this. Now we've got an expression. We can go back to our original equation, and since we've got two unknowns, we have to have two equations. So we're well on our way. So once we do that, of course, we can do some substituting of that equation 1, this expression, into equation 2, and then as you can see, we've got everything in terms of A. So now we can find A. We have two values of A, since we've got a nice little quadratic there, and then we can do a back substitution and find our values of B. So we've found our slope, we found our A, we found our B, and pretty much now what we can do is talk about you know, our the roots of those particular equations. So the textbook, again, it doesn't work to 4 decimal places. Just so for consistency, I've been working 4 decimal places. So there is a slight difference, as you might imagine. The textbook is saying this is what they've got, and this is what I've got. So there's round-off errors, as I say. But the point is that if we use the textbook values, and again, just looking at that particular point, and we're trying to find the gain at that particular intersection point. So therefore then plug in, as usual, just using the basic equation from definition of root loci and how the gain has that value. We find that it's got a gain of 162.5650. Now this differs slightly from, you know, the textbook. Again, it's just a round-off error. The technique is what's important. Following the process is what's important. And that's why being consistent and carrying through those number of decimal points, that should work. So again, if I use my numbers, you'll find that I end up with 161. So again, it's just a slight round-off error. The technique is important. So what the next part of the process is that we need to determine the position of the third pole. So first of all, let's consider the effects of adding a pole and a 0, because those effects are quite significant. Now, we may mention beforehand that adding a 0 tends to pull the root locus towards the left. So that is, it tends to make the system more stable, and therefore the settling time is far less, so it settles much more quickly. If we add a pole, it tends to pull the root locus towards the right, as it tends to make the system less stable and settling time takes longer. So positioning a pole near a 0 and a 0 near a pole tends to reduce their effect. In other words, we get that pole-0 cancellation occurring. So for K equals 164.6, where's the third pole location? So the closed loop transfer function, T of S, of the unity feedback system, we go back to that. We were able to derive that before. We know that our gain is 164.6. So what we're going to do now is look at our characteristic equation. Now you can use Wolfram Alpha, you can use a calculator, but in this case, when I go and do that, I'm able to find my roots of that equation. So therefore then, these are now my factors. Use of brackets, this is very important. And so collating this information, we're able to plot the root locus, considering that the pole root is at S equals negative 11.6207. So when we do that, plot that out. So now we're starting to, as you can see, we've got our poles plotted out. We've got sort of some sense of our root locus. We know where this particular, the crossover point, which is occurring between the root locus and the damping ratio line. And of course, we know what the gain is at that particular value. We've just been working through those things. Now, as an aside, note that the poles lying close to the imaginary axis are known as dominant poles because their response components persist for much longer than those deep within the left half plane. There's often the need to simplify a system model. For example, here we are working with a third order system model and approximating it to a second order system model. So it can be done by retaining only the dominant pole pair, provided that the third pole is sufficiently well separated from the dominant pair. So how far is far enough to discount this third pole? The rule of thumb is that if the pole's real part is 5 times the real part of the dominant poles, then the system can be approximated as a second order system. So here is a third order system. The system has 3 poles. Is the system a valid second order approximation? Okay, so if we take that into account, consequently the distance the dominant second order poles are from the imaginary axis j omega is 0.63. while the distance to higher order poles is about 11.6207. So the dominant second order pole in comparison to the higher order poles is 11.6133 divided by 0.6934, so it's about 16.7483. So in other words, since the distance of the higher order pole more than 5 times, the distance of the dominant second pole orders from that imaginary axis, j omega, then that validly is a second order approximation. It's a good thing to check. Just the textbook flies over some of these things, so I just want to help validate that and provide some clarification. So if our gain K is chosen to obtain that damping ratio of 0.174, consequently K is equal to 164.6. So the position constant Kp, again going back to what we did with steady state errors, we can calculate that. Kp is 8.23, and with the unit step input we said beforehand, so plug that in, we're going to find that that equals 0.108. So the value of the step input is 1, but since we have error occurring, the output that we are getting from the system is going to be 1 minus 0.108, which is about 0.892. So consequently, we can see we've got a reduction or an improvement in the steady state error using that technique. It's slight, but it definitely is a reduction. So the real issue is to reduce the steady state error to 0 without greatly affecting that transient response. We reduce the steady state error by increasing that system type, if you remember. So in order to increase the system type, we will need to add poles at the origin. In order to ensure the transient response does not change, we'll also need to introduce a 0 very close to that compensated pole, the pole of the origin. So we get that 0 pole cancellation occurring. The angular contribution of both the compensated pole and the 0 will cancel each other out, thus maintaining the original transient response through pole 0 cancellation. Okay, so going back, here's our compensator now, compensated system. So by adding that integral, ideal integral compensator with a 0 at z equals negative 0.1, we can consider the open loop function such that we can go through, plug that in. I'm going to do exactly the same thing now, such that generating that feedback, unity feedback. So we end up with this expression now, which is a 4th order expression, as you can see. Again, that's going to give us that characteristic equation. So that's s to the 4th plus 13s cubed plus 2s squared plus 20 plus ks plus 0.1 k. So another section of the compensated root locus is between the origin and that 0 point which is really S equals negative 0.1. So repeating the process again to determine the value of the gain, exactly the same process. We're going to do exactly the same thing again. So graphically, that's what it looks like. We're looking at those angles again. So as you might imagine, we've got to go through and do that process again. We follow that through, and if we follow that through, we basically end up with these two values. Now I'm going to use the textbook values, but when we do that, it gets a corresponding value of K equaled 158.2. And again, we search the region with this value of gain. The fourth closed loop pole can be determined to be located at about negative 0.0902, which is close enough to the zero to cause pole zero cancellation. So consequently, the compensated system's closed loop poles and gain, which indicates that transient response of the compensated system, is about the same as the uncompensated system. However, the compensated system with its pole at the origin is a type 1 system, unlike the uncompensated system, which will respond to a step input with a zero error. So basically, we plot in now all our values, and we've been able to plot in our fourth closed loop. We've got, you know, that particular, looking at across from our damping ratio line, our new zero occurring here at the origin. Well, it's so close to the origin, doesn't matter, but we're getting cancellation from those things. So the figure below, coming up, compares the uncompensated response with the ideal integral compensated response. Step response of the input integral compensated system approaches unity in the steady state, while the uncompensated system approaches 0.892 as we calculated. Thus, the ideal integral compensated system responds with zero steady state error. The transient response of both the uncompensated and the ideal integral compensated system is the same to approximately 3 seconds. So after that time, the integrator in the compensator slowly compensates for the error until zero error is finally reached. So as you can see, in about 3 seconds, saying up there. So this is the figure that we're talking about. So uncompensated, the black line, the blue line is the ideal integrator compensated. So after that time, after that 3 seconds, the integrator in the compensator slowly compensates for the error until zero error is finally reached. Now, the simulation shows it takes about 18 seconds for that compensated system, so about 18 seconds, for the compensated system to reach within plus or minus 2% of the final value of 1. While the compensated system takes about 6 seconds to settle to within plus or minus 2% of the final value of 0.892. The compensation at first may appear to yield deterioration in the settling time. However, notice that the compensation reaches the uncompensated final value around at the same time. So the remaining time is used to improve the steady state error over that of the uncompensated system. So, collating this information, we can see that our plant and compensator, if we have an uncompensated system, there's our compensated system. Percentage overshoot, well, that's going to be exactly the same. Our gain, yes. Our dominant poles, and where we've got our third pole, fourth pole. So therefore, we can see that our compensated system produces a zero error at the same time the coordinate of the dominant second order poles and the higher order poles for the compensated and uncompensated system configuration is almost the same. Huge differences there, which highlights that the transient response for both compensated and uncompensated system configurations is almost the same. The only difference is that the system has a zero steady state error. Okay, so mission accomplished. So that was for the analog system. In the digital system, well, as you might imagine, we can do similar things. So we can now discuss designing digital compensators like that discussed for the analog approach. Rather than designing directly in the Z domain, the approach adopted is design in the S plane and then transform our S plane design to a digital implementation. We previously used a bilinear transformation to analyze stability, and we'll look at that. Here we'll continue with the S-plane analysis and design by applying it to a cascade compensator design. Note that a direct design of compensators on the Z-plane is left for obviously a far more dedicated course to do a digital control system. This is just an introductory. So cascade compensation via the S-plane. Now, in order to perform that design in the S-plane and then convert the continuous compensator to a digital compensator, we'll adopt that use of that transformation, or the Tustin. This process will preserve at the sampling instances the response of the continuous compensator. Now, this transformation is a technique which yields a digital transfer function whose output response at the sampling instance is approximately the same as the equivalent analog transfer function. So doing, the Tustin transformation transforms the continuous compensator, GC of S, to the digital compensator, GC of Z. So S. This is the particular transformation process. We've seen this before. So after the sampling interval gets smaller, that is a higher sampling rate, the designed digital compensator's output yields a closer match to the analog compensator. If the sampling rate is not high enough, then this is a discrepancy at higher frequencies between the digital and analog filter's responses. These discrepancies are able to be compensated for, but we need to do, we don't deal with that in this particular unit. Astrom and Wittenmark, they've developed a guideline. So when you're selecting your sampling interval, they conclude that the value of t in seconds, our sampling interval, needs to be in the range of 0.15 omega phi m through to 0.5 divided by omega phi m. Which is of the magnitude frequency response of the cascaded analog compensator. So we'll look at that as we go through. Okay, let's have a look at an example. As always, that's the mathematical background. Here we have a digital system. We've got a input of RFS, we've got an A to D converter, an analog to digital converter. We've got a digital computer, finish with that, and we've got to convert back from digital to analog, and then basically go through our plant. So in this case, let's choose a plant. GP of S is our transfer function, is equal to 1 divided by S into S plus 6 multiplied by S plus 10. The required digital system is to operate with an overshoot of 20%, and using the analysis from example 9.6 in the text, basically they were able to show that with those conditions of overshoot and particularly settling time, the lead compensator is determined to be GC of S equal to 1,997 into S plus 6 divided by S plus 29.1. So we're going to use that as our basis. So what are we going to do? We're going to design a digital lead compensator, GC of Z, as shown in the figure below, so that the system will operate for these conditions of overshoot and settling time if our 0 dB frequency is 5.8 radians per second. Okay, so a compensator, a plant, we've got unity feedback. Let's see how we go about doing that. Now we're going to adopt the process outlined above, whereby we create the design in the S-plane and then transfer the compensator to the Z domain using the Tuscan transformation to obtain the model for an equivalent digital controller. So we commence by considering the configuration of our continuous system used for our design process, and there we have our lead compensator and our plant. So in order to determine that sampling interval, we said we're going to go and use that Astrom-Wittenmark approximation. So if we do that, it's going to fit in between those two particular range, that range of values. So again, we were told that this was 5.8. So therefore, we're saying that it's got to fit between that particular range. So using this range of values, let's adopt a sampling value of 0.01. I'm going to follow the textbook so that we can compare our solution to it. Now recall that the Tuscan transformation transforms the continuous compensator, GC of S, to the digital compensator, GC of Z, which is of that particular form. So that's our transformation. This is a GC of S that we were given from that other design features above. So we're going to plug in our transformation, as you can see, and now it's sort of algebra to get common denominators, multiply through, and as you can see, that's pretty much what the form of our GC of Z is. And as you can see, we've got a T value in there. In this case, we're going to evaluate at the time interval of 0.01 seconds. Again, plug in your numbers, reduce it, and they do interesting things as you get down to here. You'll see that what they do is they tend to divide through by whatever's in the characteristic equation. They tend to take the highest power and divide through by that. So I've just followed the same process. So the textbook's slightly rounded off, but the process is correct. The key thing is the process. So that's what we end up getting. So this form of G of S presents a common occurrence in digital control systems that we've talked about beforehand, namely that we have a transfer function in cascade with a zero-order hold, and we can develop a general solution to that category of problem by moving the S in the denominator of the zero-order hold to the plant transfer function. So nothing new there. Then we take the transform, define the Z transform. So again, following through that process as we've done beforehand. Now, concentrating on the second term. Okay, we're going to concentrate on this term now. We need to generate that partial fraction. So to do that, we need to always check, we'll expand it out, then as always, check it as a proper fraction. So it's a proper fraction if the degree of the numerator and is lower than the degree of the denominator. So that is, so we don't need to, we can see here that the highest power is s to the 0, highest power here is going to be s to the 4th. So that's no problem, we don't have to do anything fancy to divide through. So by our partial fractions, again from our first year mathematics, that's how we do our partial expansion. Then so we're just going to follow through, again, follow through that process. We end up with, we've now got the same common denominator, so we can start evaluating whatever our coefficients are. So again, we've got some simultaneous equations now. We've got 4 unknowns, so we've got our 4 equations, which we do have. So then we go through, we can see that A is equal to -1 divided by 225. Keep working, and we're able to find our values for each of our terms. We found D is -1 on 400. Back substitute, we see C now, so we found all our values basically. So follow through that mathematics. So now we can plug that back into our equation again for our partial fraction. So our partial fraction looks like this, and then consequently, just as we've done beforehand, we need to take our Z transform of that. So we end up with, as we look up our Z transform table, so it ends up with that form. And then if you remember, we're taking a sampling of t equals 0.01. So continue the process. You just got to go through now and follow through with that process. And you should end up with your plant looking like that. Again, we've got very small numbers, so you're going to end up with a round off error of some sort. But I'm going to use the textbook values so that it matches with their figures and that type of stuff. So the time response is in the figure below for t equals 0.01. It shows that the compensated closed loop system meets the transient response requirements, and this figure also shows the response for the compensated design with sampling times at the extremes of that guideline given by Ostrom and Wick and Marks. All right. Now, as I say, it's an introductory unit. The key thing is that follow through the mathematical processes. You'll see that with the analog process, underlying factor is the root locus that we've used and the principles and the mathematical characteristics of the root locus. The tutorial problems you only have 2 tutorial problems for this particular session. So as I say, it's introductory. So we just want to concentrate on giving you some insights into designing control systems using compensation techniques.